Firstly, computers. They're brilliant. And they're doubling in power about every 18 months according to Moore's law. But the problem is there are some things that ordinary computers are very bad at. For example, trying to work out what numbers you have to multiply together to get a big number. Using a standard computer that we've got at the moment, which we call a classical computer, if you wanted to work out what prime numbers were multiplied together to get this, you'd have to go, was it 2? No. Was it 3? No. Was it 5? No. You have to keep on going through all of the numbers, which when you get really, really high numbers, takes an awfully long time. And this is actually the basis of a lot of security on the internet. And there are a lot of other problems about this, like this, which actually it would be useful to solve, working out, like for instance, the shapes of proteins based on the neutron and X-ray diffraction data we get. So what we'd like is what we call a quantum computer, where instead of checking every single number, we will check lots of different prime numbers, effectively all at the same time, and just get the correct answer out. And the way we can do this is because we use, instead of bits in computers, which are either 0 or 1, we can use quantum bits or qubits. And these can exist as zeros or ones or a mixture, because quantum things can be in a mixture of different states. And that's important, and we'll come back to that later. But to make these qubits, one way of doing it is using photons, which are the smallest possible amount of light that you can get, and you can't split them up. And my job is to make those using a semiconductor called gallium arsenide. And to work out how we make this, we've got to look at the electrons inside gallium arsenide, and we have one simple equation. This is our one equation. You don't need to really know what these bits are, but this V is sneaky, because it effectively says, add the rest of physics in here. To solve the equation properly, we need to know the position of every particle in the known universe. Luckily, we don't actually need to, because most of them are outside the semiconductor, outside the gallium arsenide, so we can just ignore them. But that still leaves us billions upon billions upon billions of particles inside the gallium arsenide that we need to actually take into account. So we give the mathematicians this big equation, and we say, just average out the effects of all of those, and give us a nice simple equation for the movement of the electrons in there. And they do that, and they give us this. Which basically says, this star by the V means you can ignore everything apart from the potential that you're actually putting across it, the voltage that you're putting across it. And this mass basically says, actually, you're moving lots of electrons at once rather than one electron, but it looks like you're moving just one of them, and it looks like it's got a bit lighter and easier to push around. The other thing that happens is we get this what we call a band structure. As you go up the screen, the higher it is, the higher energy the electrons have. At the top, there's a band full of energies that they can have. At the bottom, there's a band full of energies that they can have, and the gap in the middle is not a band. That's a place where you cannot have any electrons of that energy. And what I do is I actually put another material, another semiconductor called indium arsenide in the middle to create this little kind of kink in the band. So now we've got some places inside this tiny, tiny blob of indium arsenide where we can have electrons. And if we catch an electron in the top bit with lots of energy, it can lose energy, fall into the bottom one, and give us out just one particle of light. And when I'm trying to get this to happen, when I apply a voltage across it. So I'm trying to make, effectively, the world's best, worst LED. and how do I go about this? First thing is I do all the calculations and design something. Then I get this grown for me. So there's a machine called a molecular beam epitaxy machine, which very, very slowly deposits atoms on top of each other. To grow this bit in the centre, we have to deposit it at less than one layer of atoms a second. Luckily, if we do that, this bit, the island of this lump of indium arsenide, it just clumps together naturally, which is great. What's not great is the machine that we needed to do this slowly broke, and I couldn't do any experiments for a year. So that's one of the downsides of being an experimental physicist. Another one is what you have to do afterwards, because to turn it into an LED, we have to use lots of acids to actually etch away all the bits that we don't want, and so we can put some metals on the top to be our electrical contacts. And this is what, from the data sheet, the hydrofluoric acid, which we use. Key things that you'll note is it readily penetrates skin, causing destruction of deep tissue layers, including bone. This process may continue for days. So even though, unlike some physicists, I'm actually using my hands and making things, and in a sense getting my hands dirty, getting your hands dirty is very much not what you want to do with this stuff. So that's one problem. Well then, what I've got to do is, if you just look at this, we've got to actually cool our sample down really cold to only a few degrees above absolute zero using liquid helium. Because otherwise, imagine you've got lots of, say, Cub Scouts running around. I'm a scout leader, you get that. And as a start, they've got lots of energy, they're running around all over the place, and that's like them being hot. And if you try and get them to stay in one place, they won't do it. They'll go running about. But if you do some sort of game which tires them out and takes away the energy, which is effectively lowering the temperature, they will actually stay in one place. So I have to do all my experiments inside liquid helium. And what experiments do I do? There are two key experiments. This one is the worst LED test. This is to make sure that we're only ever getting one of these tiny particles of light out at any one time. And the way we do this is we look and say, can we count two particles at the same time? No. Probably got one then. And we do this with, we've got two detectors, in which you can each pick up one of these individual particles of light. And we've got this, what we call a beam splitter. And when the particle of light comes in here, if there was lots of light, half of it would go one way, half of it would go the other. But we've got this tiny amount of light that we can't split, and so it can only go one way or the other. So if we've got one of them, we can never actually see two clicks on these detectors at the same time. And this sad-looking graph is one of the key results of my 5-year PhD. The fact that there's a dip at time equals 0. It doesn't even go all the way to the bottom. If it was perfect, it would go all the way to 0. This kind of sits around 0.25. So it's good. That's at least half of it. But there's another thing that we want. And in the quantum computer, all these particles of light have to interact with each other. And so if we're using my source, we want all the particles of light to be exactly the same frequency, exactly the same colour. Because if they're different colours, then they don't interact so well. And we can test how well my sample makes these by performing the best LED test. And this is really, really confusing because it's about quantum physics. Remember when I told you earlier that quantum can be in two different states at the same time? You all get that, yeah? But they can also be effectively in two different, they can also be created at two different times. That's the same one particle appearing at two different times. So I'm going to use pictures of the Doctor because it's almost like a weird form of time travel. Some light will come out of my sample and go down the long arm here, and because it's long, it takes a long time for it to go out there and bounce back. A little bit later, some other light, hopefully exactly the same, will come out there and bounce down this arm. And then they will both meet at the beam splitter again and interact. And we can, because they're light, it's a wave, they can join together and make the wave bigger, they can cancel out, and the bigger the interaction, the bigger the difference between adding together and cancelling out will be. And we can measure that, and so that will give us a nice big point here, close to 1, that means it can almost cancel out. But if we increase the delay, we still have our first particle, but my sample, my source, has wobbled a bit. The electric field in it has changed slightly, and so it actually gives out a slightly different colour of light. And these two, because they're different, when they both hit here, are going to interfere in a different way, and not as well. But the key point to remember is, just like the Doctor being the same person, the things that are interacting here are the same particle of light. It's existing in these two separate places, but when we measure it, we only ever measure it once. And yeah, if you find this confusing, don't worry, because it's often said, if you think you understand quantum physics, you don't. So it's completely weird. But basically, the amount of time that this delay can be, the longer the delay that can be, the better the source is, the more reliable it is, and hopefully we can use it in quantum computers. And there's one last thing. There is a quantum computer that's being used using light, sadly not using my light, but it does exist. We haven't quite managed to factorize a large number like that, but the state of the art so far, we've managed to factorize 15. Thank you very much.